Okay, let me continue. So, how to compute the gradient of the deep neural network? So to understand this gradient, calculating gradient, we need the new concept of the computation graph and backpropagation, right? So if you go back to our lecture 9, maybe, so we discussed this one here, right? So if we just think about just the one layer, the input of this one layer is the x, and the network parameter w here, and output is here h, then the upstream gradient is the gradient of the L in terms of the h, right? And the local gradient of the h of w and h of x. Then by using these two upstream gradient and the local gradient, and we can generate the downstream gradient, right? Something like this. So it was the general idea of the computation graph and backpropagation, right? So let's recap what we have done so far. So what do you want to do here? We want to estimate the net gradient of the loss function in terms of the network parameter w, right? So in this case, let's say this is the network parameter w, network parameter, and this is the input signal, and this is output of the one node here. So in this case, let's say this is just one gradient, right? If you remember this one, so one convolution layer, right? And ReLU layer here, right? Any kind of the node or the block in the deep neural network can be generalized to this computation graph, right? So what you want to do is, if we compute the loss in terms of h, then we can get the loss over w, gradient of loss over x. So, and then to compute this one, we will use the local gradient x by h, w by h here. So in this case, h w, something like this, right? This one will be used, this one, and this one will be used here, right? To finally get this one. So yeah, what about this? Will be h over lxh, right? So this one is used here, and this one is used here, right? So compute this one, right? So this is just called the chain rule. We already discussed this one in lecture 9, right? Then by using this local gradient, we can update this w using this stochastic gradient descent, right? Here, right? Then why we need this local gradient? Why we need this one? Because if we compute this gradient in this layer, then we have to backpropagate the loss gradient from loss layer to the shallow one. Then by using this local gradient, we can we can do similar thing to another previous layer here. So it will be the next upstream gradient to the another layer, right? So this is the concept of the computation graph and backpropagation, right? So by using this backpropagation, we can efficiently estimate the local gradient per each parameter samples from a low layer to high layer, right? So this is the general idea of the computation graph and backpropagation, right? So let's see the example. So this is very simple. Convolutional neural network. Okay, so let's say we have the training data set x and y, right? X is input, y is output, right? The problem is to find the parameter w. So in this case, the parameter w consisting of the parameter 1 and parameter 2. The w1 is for the first convolution layer. The w2 is second convolution layer, right? Then that minimize the loss function lxy given w here. So this is input, output with the loss function here. So training this convolutional neural network means to update this W1 and W2. So it means that we have to find out the gradient of loss function in terms of W and gradient of the loss in terms of the W2, right? Then how can we do that? As I mentioned previously, compute this one directly is really hard to compute when the network is really big. So we need backpropagation and chain rule, right? So how can we do that? First of all, we can compute x3 xl, right? So it is really easy, right? Because this L is defined as a function. Okay, let me use this L, small l, function of x3 and y, right? So we can easily compute this one. Then what do you want to do next? Because in the convolution layer, we can easily compute the gradient x3 by x2 and gradient w2 by x3, right? Then in here, x3 by w2 by x3, right? So we can compute this one like this, right? So by the way, x3 is the convolute with the xw2, right? So if you remember the convolution definition in our lecture 10, where is that? Lecture 10. Here, right? So if you remember this one, by computing the derivation in terms of the f or in terms of g, we can easily generate the f2 x3 and w2 x3. So please derive this one is yourself, right? So it is really easy, right? So anyway, so we have now we can compute x2l, right? So how can I compute this? x3l x2 x x3 here, right? So this one will be used to another loss gradient, right? So then there is a value, but there is a value term, right? So in value function there is no learnable parameter, right? So we can just backpropagate this gradient to the x1, but here we can also compute the x1 over x2, right? When x2 is max x1 0, right? So derive this one is also yourself. It's up to you, right? So anyway, we can generate x1 and xl here, right? So there's one more gradient, one more convolutional layer here. Then we can also compute del x1 and w1 x1, right? So finally, it will be x1 xl in w1 w x1, right? So by using this one, we can update this w by using the stochastic gradient descent, right? So from here, this one is related to here, related to this one, right? This one and this one, right? So it means that compute this one, this whole gradient, subgradient are connected and used to compute this one. So this is why this network, this computation is called the chain law. Okay, chain law. Right. So this is the overall procedure to train the deep convolutional network. Actually, this is very simple version because there is only two convolution layer with the one value function. But if you have the more convolution layer with the more difficult network, you can do this similar. You can do similar things in your neural network, but as I mentioned previously, you don't need to compute this one, but because your network, your library will do this, but please try to derive this one yourself to understand what's going on in your network. Okay, so this is the compute the gradient. So yeah. So give me 1 minute. Okay, so let's continue. So if you think about the more difficult neural network or the more complicated neural network, let's see the examples of the GoogleNet, or called the Inception version 1. As you can see here, there is the input and there is the convolution layer, right? So if you remember our previous slide, so this is the 7x7 filter with the stride 2, right? And here's the max pooling here, and this is a local normalization. We will discuss this later, but and there's one more combo normalization and max pooling, and there are several streams here, right? So blah 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 blah. So it looks really hard to compute. So please think about how can you compute this gradient. So let's say this is W, and how can I update this one in terms of this loss function here? How can you do that? So as we discussed previously, you can, first of all, you can just port the input xn through this network parameter, and then you can compute the backpropagate in terms of some arbitrary x with the L, right? So by backpropagating this cycle, you can finally compute this one in terms of W. Okay, so this is the general idea to compute this network, right? So this is the main idea of the calculating gradient. Okay, so what do you want to do next? So now we have the way to compute the gradient and way to update the network parameter. And what do you want to do next? Okay, so we need a more clever way to improve the stability of training the neural network. So there are several kinds of techniques. The first one is the normalization. So why we need the normalization? Okay, let's draw our original sample xn, something like this. So the shape of the original our input features, or the distribution of our original data sample xn is something like this, right? So before normalization, if you think about the classification laws very sensitive to change in weight matrix and hard to optimization, right? So what do you want to do first? We want to normalize data, something like this, right? So comparing this one, okay, let's say this is the x bar, right? So in this case, it has the zero gradient with the one standard variation, right? So after normalization here, the less sensitive to the small change in weight and easier to optimize. So frequently we use this pre-processing of the original data to make the training more tractable, right? So there are several kinds of ways to process the original data, but you can easily think about this, subtracting mean by normalizing the covariance, right? So this is the simple way to normalization data pre-processing, right? Then what next? There's one more very interesting concept called the batch normalization, right? So what is the batch normalization? Actually, the batch normalization is really hard to teach you, because there's no proof why this batch normalization works well, because this batch normalization paper is published in ICML. It was ICML 2015, right? So this is also very recent technique or paper, but so there's no strong proof why this batch normalization works well. But nowadays most recent deep neural network use the batch normalization because it guarantees the stability of the deep neural network. So in here we will just understand what can we do in batch normalization, but I would say there's no proof, there's no guarantee, or there's no proof why this batch normalization works well yet. So okay, so let's try to understand what does it mean. So first of all, batch normalization is try to solve the intercovariance shift problem. So internal covariance shift problem means the change in the distribution of the network activation due to change in the network parameter during training. So it means that the network parameter W will be okay. So let's draw. Okay, let me draw this network parameter W here, right? So as evolving the iteration, network parameter distribution might be shifted here. Why? Because there are several kinds of reason of this shifting, right? So because of this shifting, it will be the problematic for the deep neural network. So in batch normalization, the authors try to solve this internal covariance shift. So how can we solve this internal covariance shift problem? If we can normalize this activation as a zero mean and unit variable variance, something like this, we can solve this internal covariance shifting problem, something like this, right? So how can we do that? We can just use the zero mean and unit variance by subtracting the zero mean and variance. So in this by applying this one, we can make zero mean and zero mean means zero and unit variable sigma y 1. Okay, zero mean and unit variable, right? So by using this kind of concept, we can solve this internal covariance shift problem. Actually, this is very intuitive, right? So if you see the detail, okay, let me say we have the n by t matrix X here, right? So it will be any kind of the activation map, right? So first of all, we can compute the per channel mean, right? Per channel means is defined by the summation of the every xin here divided by number of n, right? So this is just the mean. So in this case, the shape of this mean is the d dimension, right? Then what about the variance? To compute the variance, we have to subtract this mean for each xij and compute the square of this one and aggregate this one, right? So it'll be the sigma square j, right? This is just the per channel variance, whose shape is the d, right? Then by using this one and this one, we can just normalize original xn by using the mean and variance, right? So it will be the new I, j, right? So this is just the batch normalization, right? So this is very intuitive, right? But here is the problem, right? What if the zero mean and unit variance is hard of the constraint, right? So it means that in some case, this unit gradient, this unit variance and the zero mean will be not an optimal how to say, it's not an optimal network parameter, right? So in some case, this network parameter may be optimal. Right? So okay, so if we go back to the starting point, we want to solve the internal covariance shift problem, but if we make the zero mean and univariance, if we try to make the input vector x as a zero mean and univariance, there might not be the optimal training parameter like here. So we need another term to solve this problem, right? So yeah, here we introduce the learnable scale and shift parameter, alpha and beta, gamma and beta, right? So it means that from here we can shift this one by using learnable parameter gamma and beta and generate the yi comma j in another space. So what does it mean? Okay, let me say there is the training parameter set here. By using this normalization, we can make this one in univariate space. Then by using the gamma and beta, we can reshift this one to the another space. So we hope by training this gamma and beta, the new learnable parameter here is much optimal than the previous one or original one, right? So this is the main idea of the batch normalization, right? So at the testing time, actually you don't need to compute this one, right? Because this mean and variance is defined for the mini batch here, defined on mini batch. So you can compute this one. You can compute this one in training time. So at testing time, you can use the learning average of the values seen during training and learning average of values seen during training for mean and variance, right? So it means that we have to memorize those kinds of the average values during training, and then by using this one, we can generate the new yn from the xn, right? So this is the testing time of the batch normalization. During testing, batch normalization become a linear operation, as you can see here. So it means that it can be fused with the previous fully connected or the convolutional layer. So as you can see here, this is just the plain convolutional module with a ReLU, But as you can see here, this batch normalization here can be inserted after fully connected or convolutional layer before nonlinearity, such as ReLU. Right? So in nowadays, most deep neural network-based method use the batch normalization to make the deep network much easier to train and to improve the gradient flow and to allow the higher learning rate and faster convergence. And by using the batch normalization, network become more robust to initialization, act as a regularization during training, and zero overhead at testing time. Because you can just use this learning average value seen during training, so which can be fused with the convolution layer, something like this, right? So this is the general idea of the batch normalization. Okay, I will finish this one with a very interesting paper published in ECCB 2018. 2 years ago. So actually, this Kaiming He is the same person who developed the residual network, right? So actually, he's a really smart guy in deep neural network. Anyway, so if you think about the batch normalization here, to compute the batch normalization, we should compute the average and gradient variance, right? So then the dimension to compute the average and derivation, the batch normalization is something like this, right? But by defining the local window to compute the average and derivation, the batch normalization can be modified into the layer norm and instance norm, the group normalization, right? So in some case, in some application, the instance normalization is better than the batch normalization, or the group norm is better than the batch normalization or the instance normalization. So please, I suggest to you to read this paper to understand those concepts of the normalization during training our network. Okay. So yeah, so this is the end of the batch normalization. Then we will see the other technique to stabilize our training data set. Okay, our training procedure. Okay.